Chapter 1 of A Natural Approach to Chemistry, Section 1, What Chemistry is About. Science seeks to answer questions about the world around us. Some of these questions include, how can a seedling become a tree? Where does the matter come from? If the matter came from the soil, why don't we see giant holes in the ground? Something has to happen, chemistry, to change molecules from air into building molecules for trees. We see that most of the matter in trees, in the form of glucose, is formed from the carbon dioxide found in air, and only some of it comes from water in the ground. Let's look at another question for science. Is fire a chemical, matter, or energy? Again, something has to happen that causes something to burn and produce fire, and this something is chemistry. Fire is the result of matter changing its form, usually a carbon-based substance combining with oxygen to produce carbon dioxide. This reaction releases energy in the form of heat and light. Chemistry can help answer other questions too, like why are we encouraged to eat foods that are high in antioxidants? Antioxidants, chemicals that are found in berries, can bond with free radicals, another chemical in our bodies that can be harmful. Studying chemistry can help us understand why too much of certain vitamins, like iron, can be as harmful as too little. Nutritional biochemists help to determine the recommended daily allowance, or RDA, for each vitamin. As you already know, most of your body is made of water. Why is water so important? Many chemical reactions and physical changes take place in water because many molecules can dissolve in water and then freely move around, allowing chemical reactions to take place. There are millions of chemical reactions taking place in your body right now. In order to communicate results clearly and effectively, it is important to use clear standards of measurement. This means we all use the same measuring units for characteristics like mass and volume. When asking questions like, how heavy is an egg? How much space does an egg occupy? Does an egg-sized piece of metal or wood have the same mass? How hard is it to crush an egg by squeezing evenly from all sides? It's important that we use standard language to describe our answers so everybody understands what those answers mean. The question, how heavy is an egg, needs to be answered using a standard measure of mass. Keep in mind that the size of an object doesn't necessarily tell us how much matter it contains. Mass and volume are not the same. Let's make a comparison. Which has more mass, a 1-liter water bottle or a single peanut? It would probably help to know what units we should use for measuring mass. It would be ridiculous to say that the mass of a single peanut is 1 peanut and the mass of a 1-liter bottle of water is 1 bottle of water. How do we compare the two to each other? We need one standard unit of mass. The standard unit used for mass in chemistry is the gram. Knowing that the mass of a 1-liter bottle of water is 1,000 grams and the mass of a single peanut is 1 gram helps us compare the masses of these two items rather easily. Remember that the size of an object doesn't tell us how much matter there is. For example, it takes about 1 cubic meter of air to equal the mass of 1 liter of water. Even though their sizes differ greatly, their masses in this case are equal. The question, how much space does an egg occupy, needs to be answered using units of volume. The standard unit of volume that we will be using is the milliliter. More familiar units of volume like teaspoons, cups, and gallons are English system units that we do not use in science. The tool that we use to measure volume is called a graduated cylinder. Graduated because it has graduated measuring lines that gradually increase, and cylinder because, well, it's cylindrically shaped. If you you remember back to solving certain math problems, you may recall that volume is calculated by multiplying length by width by height. This calculation involves multiplying 3 units of length. In science, we typically use a length measurement system based on the meter. A milliliter is equal to 1 centimeter cubed, a distinction that helps us relate standard length units to standard volume units. In order to answer the question, does an egg-sized piece of steel or wood have the same mass? We need to understand the concept of density. It may feel intuitive to answer that the steel has more mass than a same-sized piece of wood, but how can we describe that difference? In this diagram, we see 3 blocks of different substances, but with equal volume or size. According to the balance, the plastic has a mass of 0.9 grams, the glass a mass of 2.7 grams, and the iron a mass of 7.8 grams. How can we use this information to describe the comparative heaviness of each? The quantifiable relationship between mass and volume is called density and can be calculated by dividing the mass in grams by the volume in cubic centimeters. Remember, 1 milliliter equals 1 cubic centimeter, so density can also be called grams per milliliters. Let's see how we can apply our understanding of density to answer this question. If 45 grams of titanium are added to a graduated cylinder containing 50 milliliters of water, what will the cylinder read after the titanium has been added? In order to solve this problem, we need an additional piece of information, the density of titanium. Given that titanium has a density of 4.5 grams per cubic centimeters, which remember is the same as milliliters, how much volume would it add to the water already in the graduated cylinder? Take a moment to try this calculation. Even though we're given that density is equal to mass divided by volume, we actually want to solve for volume. We need to rearrange the density equation to get volume by itself. Then we'll plug in 45 grams for mass and 4.5 grams per cubic centimeters. Again, cubic centimeters equal milliliters, and solve. Our answer tells us that the 45 grams of titanium will take up 10 milliliters worth of space, which should cause the water level to rise from 50 milliliters to 60 milliliters. This method of measurement is called displacement because we are using the displacement of the water by the titanium to make measurements. In order to answer our final question, how hard is it to crush an egg by squeezing evenly from all sides? We need to understand what pressure is. Although we talk about pressure all the time, we typically don't think about its formal definition. Pressure is defined as the force applied on a specific unit area. Understanding pressure helps us explain how we can inflate rubber tires and then use the air inside to cushion our bike ride. It's important to note that pressure acts in all directions equally. If holes are punched in an air tube, the pressure inside will cause the air to rush out of each hole equally. A force which causes pressure can be thought of as a push or a pull. Pressure can be measured using various units, such as pascals or pounds per square inch, depending on the context of the measurement. The discussion of pressure leads us to more questions. We can easily squeeze a water bottle without its lid screwed on. But can you squeeze a bottle that is tightly capped? The answer is no. The reason why we can't easily squeeze an empty water bottle with its lid screwed on is that the bottle is filled with air molecules. The air causes pressure, takes up space, which we call volume, and has mass. You experience the feeling of air pressure when you put your hand outside the window of a moving car. When we make measurements, we often use terms like accuracy and precision. In order to help us understand what those terms mean, let's look at this example. The substance on the balance shows a reading of 10.0 grams. Because the balance only reports to the nearest tenth of a gram, or 1 decimal place, The actual mass could be 9.96 grams, rounded up to 10.0 grams. It could just as likely be 10.04 grams, rounded down to 10.0 grams. There's no way for us to know without using a balance that reports to the nearest hundredth of a gram, but then we wouldn't know what the measurement was down to the thousandth of a gram. In this class, measuring to the tenth of a gram is sufficient, but in many other applications, sometimes we need even more precision. Measurements that are not accurate could lead us to the wrong conclusion. When we collect data, we want to be as accurate as possible in our measurements. We also need to be precise, so we are recording our data in a way that reflects what we are actually measuring. Accuracy can be achieved by using the measurement equipment properly and consistently. Precision can be achieved by recording the data to the proper number of decimal places as indicated by the measuring equipment. In order to achieve precision, we need to report the correct number of significant figures. In this example, the balance reads 10.0 grams. What would you record in your lab book? 10 grams or 10.0 grams? Does it make a difference? Of course it makes a difference. It makes a difference in precision. We know that 10 grams only indicates that the mass is somewhere between 9.6 grams and 10.4 grams. And that's a pretty big range. A 10.0 gram reading indicates that the mass is somewhere between 9.95 grams and 10.04, a much smaller range and more precise measurement. Here we can see a visual representation of what those differences in ranges would be. We see this is a big difference in precision. Let's practice reading volume measurements. What volume would you record for this volume of liquid? Each milliliter on this particular graduated cylinder is marked with the dash. The accepted rule is that we can estimate to 1/10 of the smallest gradation mark. For this reading, we should report to the nearest estimated tenth of a milliliter. Also remember that when measuring volume, we measure based on the lowest point of the meniscus, or bubble on top of the liquid. What is your measurement? It appears that the meniscus is right on the 18 milliliter mark, but because we can estimate to the nearest tenth of a milliliter, we would record 18.0 milliliters. The real value for this measurement would actually be somewhere between 17.9 and 18.1 milliliters. The accuracy of our measurement depends on how well we can read the equipment, in this case a graduated cylinder. The precision depends on how many decimal places our equipment is capable of measuring. Because science involves studying very large objects, like the universe, as well as very small objects, like individual molecules, we need a shorthand system to write very large and very small numbers. You're most likely already familiar with and have used scientific notation. Here we'll look at a simple number as our first example. 1,500 can be written as 15 times 100. We see that 100 is a power of 10 that can be written as 10 squared. The number 15 is called the mantissa in this example. Now let's write the power of 10 in exponent notation. The standard way to write the mantissa is to keep one digit in the ones place and to write the following digits after a decimal point. When we move the decimal to the left one place in the mantissa, we need to adjust the power of 10 notation. 1500 is equal to 1.5 times 1000, or 1.5 times 10 to the third power. The accepted way to write 1500 in scientific notation is then 1.5 times 10 to the third power. You may have learned that the exponent on the power of 10 is also indicative of how many places to move the decimal point in the mantissa. 4 times 10 to the 7th power becomes 40 million when the decimal point next to the 4 is moved over 7 places. In the same way, we see that in order for 3.6 to become 3600, the decimal point moves to the right 3 places, matching the exponent. And 8.31 becomes 83,100 when its decimal point is moved to the right 4 places, as the exponent indicates. What happens when we're looking at numbers that are less than 1? Here, 15 ten-thousandths can be written as 1.5 times 0.001. Even though it may not look like it immediately, 0.001 is also a power of 10. Exponents can be negative numbers. A negative exponent means that the number is smaller than 1. The mantissa is still one digit followed by a decimal point and any other digits present in the original number. We would write 0.0015 as 1.5 times 10 to the negative 3 power in scientific notation. A negative exponent indicates that the decimal point in the mantissa needs to be moved to the left this time, so that the mantissa number becomes smaller, which is indicated by the negative exponent. In this way, very small numbers are expressed with negative powers of 10, and very large numbers are expressed with positive powers of 10. Now it's your turn to practice writing numbers in scientific notation. Convert 0.00065 to scientific notation. If you answered 6.5 times 10 to the negative 4 power, you are correct. If you answered incorrectly, where was your mistake? Did you remember how to determine the mantissa? Did you use a negative exponent? Did you count decimal places correctly? When we use numbers in scientific notation for calculations, we need to enter those numbers correctly into our calculators. Most calculators have a button labeled EE, which is just calculator language for times 10 to the. First enter the mantissa, in this case 5.5, then press the EE key, followed by the exponent on your power of 10. Some calculators have a key labeled EXP instead of EE. These keys function the same way and mean the same thing. Another useful skill you will need is to convert between different units. You can already easily convert between minutes to hours. For example, 30 minutes is equal to 0.5 hours. You will also need to be able to use a conversion factor, such as those shown here, to convert from one set of units to another. How would you set up the conversion from $1.25 per liter to dollars per gallon? Somehow you need to convert the liters to gallons, don't you? Here we can see that the conversion factor to use is 1 gallon equals 3.785 liters. Knowing which conversion factor to use, you should now complete the conversion. When we line up what we know, $1.25 per liter, with the correct conversion factor, 3.78 liters per gallon, then multiply, the liters units cancel and we end up with 125 times 378, or $4.73 per gallon. In summary, your key takeaways for this section should be: you need to use standard units of measurement in lab. You should take care to make your measurements as accurate and precise as possible. You need to be able to complete calculations using scientific notation.